Hello, this is the second tutorial of the Real-Time Embedded Systems course. In this tutorial, we will be talking about the first hardware concept, which is the difference between microcontrollers and microprocessors. After understanding the difference between the two components, we will create a system via a virtual processor and program it on the Altera board. Okay, we will start with the microprocessors. A microprocessor is a standalone integrated circuit which processes basic instructions that drives a computer. A processor deals with any type of instructions it is given. It is not programmed for a specific or a certain task. It deals with various types of tasks, as we can see how our laptops deal with different types of programs and different types of information. It is not dedicated to a certain program or a certain type of information. For a processor to be functional on its own, it's not functional at all. It has to be connected to external peripherals as to be able to communicate with other modules, read and write data, and so on and so forth. Okay? Since the processors have to be connected to external peripherals to be functional, the resulting circuits are quite expensive and large, depending on the intended functionality. We can see the difference in sizes and prices when we see gaming laptops versus normal laptops and a certain type of computers which is called supercomputers, which are used in fast processing of big information. These type of computers require very strong processors and very strong and very fast processors because they deal with big chunk of data, and we need to process these data as fast as we can. So when we choose these kind of fast and strong processors, we have to choose very strong peripherals connected to it to make it functional and fast, and this increases the size and the price of the resulting circuits. That's why these computers are very expensive, and it's mostly used by big companies and research labs. On the other hand, a microcontroller is a compact integrated circuit which is designed for a specific task. Once the program of this specific task is embedded on the microcontroller chip, it's not easily altered, and it may need some complex steps for us to change the sole purpose or the sole task that the microcontroller does. We can see here a figure of the Arduino, which is a microcontroller. This microcontroller, it has the task of reading whatever program that we write on its IDE. It takes inputs through these pins and gives us an output through these pins. We do not program the actual microcontroller, we just upload our code on it, and it reads and it processes whatever data we have, takes the inputs from the pins and gives us the output as a result. These inputs and these outputs are expected by the microcontroller because it already has the script for it, or the code that we have already uploaded earlier before actually running this code and testing our hardware. That's the difference between a microcontroller and a processor, or a microprocessor. A microprocessor deals with whatever task that we have, different types of tasks, different types of information. The output of the processor or the microprocessor is not always expected because it depends solely on the type of data or the input of the input data. Unlike the microcontroller, as we said earlier, that it already knows or understands the type of inputs, how it will get it, and the expected kind of output, and how it will actually send it or display it. Since microcontrollers are compact integrated circuits, this means that it does not need any external peripherals connected to it for the circuit to be functional. All the required peripherals are already connected internally with the processor, which is inside the microcontroller. So the circuit is actually a small circuit if compared to the circuit of the microprocessor on its own. Plus, this also indicates that the system cost is actually low because we buy one thing and it is functional right away. We don't need to have any external components for it to be working or functioning. We now know the difference between microcontrollers and microprocessors. We will simulate a microprocessor's circuit virtually using our Altera boards, which has a virtual processor called NIOS2. For the processor to be up and running and functional, we have 5 components to be included in the circuit. The first component is the clock. We need it for sync purposes for the rest of the components. The second component is the actual processor, and we mentioned before that we will be using the NIOS2 processor, which is a virtual processor on the Altera board, available on the Altera board for these kind of simulations. The third component is a memory. The third component is input-output peripherals, which are like LEDs, switches, the normal input-outputs that we understand and know. The fifth component is the JTAG, or the serial communicator between the computer and the actual board, because we will use our board as the actual processor, so we need communication channel between the computer and the board. The circuit main task is to light up 2 LEDs via 2 switches on the board. To program the Altera board, we will be using the Quartz Prime Lite Edition program. You will not be writing any Verilog or VHDL code. We will just design the circuit itself, and the program will generate the output code, and we will just upload the code on the board and deal with it as the processor on its own as a whole. We will start by creating a new project, call it chip 1, and saving it in the same directory as it is. We're not gonna change the location. And then choose the family device, which is Max 10, and from the device name tab we will scroll down until we reach until we see our device name, which is 10M50 something, and then we will launch the platform designer, because our main task is to design the circuit and then generate the corresponding code. The program generates the code itself, and then we will upload it on the board and program the board, write our code, and then light up the 2 LEDs via the switch. We will start by having the clock, the main clock. It's already there. We will rename it to clock_main. And then from the IP catalog, we will start adding our components. The first component is the NIOS2 processor. We will add it and then change its name and add the rest of the components. We will add our memory as we mentioned. We will change its size and its name. we will add our input-output peripherals. In the code we said that we will light up two LEDs via two switches. So we need to have two types of parallel input-output peripherals here as a simulation. We have inputs and we have outputs. So we need to create outputs, which is the LEDs, and inputs, which are the switches. We will start with the inputs, which are the two switches, and then add another component, which is our output, the two LEDs. After adding the two parallel input-outputs peripherals in the circuit, we will change the first one, which is the inputs, to rename it to switches or switch, and the second parallel input-output, which is the LED, and then add our JTAG, which is the serial communication between our simulated circuit processor and our computer, which will upload that circuit to the board. And we will gonna change the name of the JTAG to be JTAG. That's it. And then we will start connecting. We have all the required components for the processor circuit, but the components are not connected together, so we need to connect them for synchronization purposes. We will connect the main clock with the clock of the processor, the memory, the two inputs and outputs, and our serial communicator, which is the JTAG. And for the reset 2, we will connect all together. We will connect the processor with the memory, and the memory with the switch, the LED, and the JTAG, because we have information goes from the memory to the processor, and from the processor to the switches, the LEDs, the inputs and outputs. So we need to connect the data all together. We will connect the data master with the memory, and instruction master to the memory. And then once everything is connected, we will assign our base address, and then change our vectors of the processor. And one last thing before generating our code, because our circuit is ready, we will set something called an external connection for the inputs and outputs, because we are saying now, or we are programming the circuit as the switches are externally, so goes for the LEDs. So the switches are triggered externally from the board. So we have actually switches not simulated in that aspect, and we have actual LEDs not simulated. So we need to have this data. So we need to export the data, which is based on our program that we will be writing later on in few minutes. So we are saying now that our switch is an external connection, and the LED is so an external connection. The switch is triggered from an actual hardware, and the LED displays on actual hardware. After finishing the circuit, all the connections, we will generate our code. and the program will generate the required code that the board needs to understand this circuit and these connections. We will not program any Verilog, any VHDL at all. We will just add these files, the auto-generated files, to our project, and then upload these files to our board, and then program our switches and LEDs. Now, after the generating is over, we will add our files to the project folder, and then we'll start with the code. After adding all the files which were generated by the program, and setting our circuit file as a top level entity, we will compile these files into the project, and then we will start assigning our pins to the switches and LEDs, which will take the input, and the LEDs which will display our output, and our clock, and then compile again and upload the program on the board. After uploading the code on the board, we will start programming our processor, which is the NIOS2, via Eclipse, which is already embedded in the program. And this processor works with C language. So using Eclipse for C, we will assign the switch to be our input, and assign our LEDs to be the outputs. Actually program it. We already assigned. We are not talking about assigning the pins. We are just we can say that we are activating the switches to be our inputs, and activating the LEDs, the output LEDs. To program our processor, we will start by creating a NIOS2 application, and this application requires information about the target hardware information. This is a file which is already auto-generated by the Quartz program earlier. We will just navigate to the directory which is in the our project folder, and then select the file, have a project name, and then we are good to go and start coding our own program. After creating the template project, we will actually run it via or run as nice2 hardware. We will not run this program on our PC or using our PC. We will run it using the nice2 hardware, which is now the board. It's running now through the board, not our PC, and it will display a message at the end after it finishes its build in the console. This shows that everything is built successfully, and it will show us nice2 console, hello from nice2. This is through the board. This is the board saying that everything has compiled successfully through me, not through the PC. Okay, and now we will create our own empty project and then work with our LEDs and switches. We will create an empty project and an empty file, a C file, and write our own programming code, programming the nice2 processor, at which this code, what does it do is it sets the switches as our input and the LEDs as an output. The LEDs are triggered by the input, which comes from the switches. And then when we will run as nice2 hardware, not our actual PC. Our actual PC will not compile the code. We are using the Altera board as if it is an actual computer or a mini PC, a small PC, to compile and run the code on it. And we have a demo at the end of this video showing when the switches are triggered, the LED actually works.